Hi everyone. So thanks for the opportunity to speak at this conference. My name is Herng and I'm a PhD candidate at the University of Toronto. So my talk is going to be about using currents to represent cohomology. So taking this algebraic topology object and finding a geometric way to represent it. So what kind of currents am I going to deal with? Let me just introduce it. So suppose that M is a compact Riemannian manifold, possibly with boundary. Then we look at the space of relative k cycles in M with the flat topology. So what this means is that if you're familiar with currents, these are the group of mod 2 integral k currents, k-dimensional currents in M whose boundary is supported in the boundary of M. If you're not so familiar with currents, you can think of them as the group of singular K chains that are supported in the manifold with Z2 coefficients and whose boundary is supported in the boundary of the manifold. So to just show geometrically what it means, that was quite a mouthful. If M is a square, then the zero cycles, when K equals to 0, these are just some set of points on the square. Well, that's it. It's just some finite set of points. And when k equals to 1, these are relative 1 cycles. So these are, you can think of them as curves, maybe a collection of curves whose boundary points, if any, are on the boundary of the square. So basically, that's what it is. And to think about the topology on this space of cycles, roughly speaking, it just means that if we take a cycle and we move it around, that is a continuous process. Okay? And if we take a cycle and we make it bigger, we make it smaller, and maybe it collapses, that is also continuous. Okay, that's all you need to know about the topology. So the key to this talk is that as a combination of two very important theorems, which I will treat as black boxes, you can take the cohomology group of X, Hn of X, which I will always use mod 2 coefficients, so I just won't write the coefficients. You can always, this cohomology group is isomorphic to this set, which is the set of continuous maps from X, which is a topological space, to the space of cycles on the n plus k dimensional cube. So k cycles in the n plus k dimensional cube or disk up to homotopy. So different maps will be considered in the same equivalence class if they're homotopic to each other. So this works for all k. It means that what's important is the codimension, right? So this is k-dimensional cycle, relative cycles in n plus k cubed. So the codimension is n. That will tell you what the degree of the cohomology group is that you are representing. So let me just give some examples. So here we have a map from the torus S1 cross S1 to the space of relative 1 cycles in a square. So if we parameterize each S1 as the interval 0 to 1 with the two endpoints identified, then this map sends S comma T to S times an interval. So as S comma T varies, you have a vertical line that's just moving around in the square. Okay, that is how you represent this. So this is, according to our previous theorem, this represents a cohomology class inside H1, the first cohomology group, because here the codimension is 1. So which cohomology class is this supposed to be? In order to find out, I should tell you how this cohomology class evaluates on the homology classes of the torus. So how does this evaluate on one of the first homology classes? Let's see. Okay, so suppose that we are trying to evaluate on this. Here we have drawn a torus. Suppose we want to evaluate this cohomology class on the homology class represented by this red loop. So this red loop, maybe it is parameterized by S1 cross 0 inside the torus. So the way we evaluate is like this. To evaluate on this homology class, you pick a generic point inside the square, and then you count how many inputs inside this red curve will allow the cycle, will allow the output, which is a red line, to contain that point. That was a lot of words, but look at this picture. So I've picked a point x comma y inside the square. So now I just want to see, okay, for how many points s comma 0 inside that red curve does the output red line contain x comma y? Well, the answer is 1, because there's exactly one of these red lines that is going to pass through that point x comma y where the input is s comma 0. So since there is exactly one of these inputs, s comma 0, that is going to so that the output is going to contain the point, we say that the cohomology class evaluates on this homology class to 1. Okay. And if you look at, it turns out that if you use this same process to evaluate this on the other generator of the homology, so there's another generator of the first homology, which is the red curve going in the other direction. If we use this same process, we will find that this evaluates to 0. So this tells you, characterizes exactly which cohomology class this map is supposed to represent. So let me give another example. Okay, this time a map that looks a little simpler. It's a map from the torus to the 0 cycles on the square. So this just sends s comma t to the point s comma t. That's it. So simple. This is supposed to represent a two-dimensional, a degree 2 cohomology class, because now the codimension is 2. So which degree 2 cohomology class is this? So to find out, we have to evaluate it on the fundamental class of the torus. So again, we do the same thing. To evaluate on the fundamental class of the torus, we have to pick a generic point inside the square, and then now we ask, okay, for what inputs does the output cycle contain our point? Now there's actually only exactly one, right? If we pick the random point x comma y, okay, yes, there's exactly one, because if we pick a random point x comma y, there is only one s comma t for which the red point is going to be that x comma 1. Yeah, it will have to be that the input will have to be x comma y. So because of that, we know that this cohomology class evaluates on this, the fundamental class of the torus to 1. And so that completely characterizes which cohomology class this map is supposed to represent. So I'm just going to point out a little pattern here. Right, now if things we know about the cohomology of the torus is that the first cohomology has 2 generators, coming from the 2 loops going in the 2 directions, and the cup product of these generators generates the second degree. So the cup product alpha cup beta, it generates the second cohomology of the torus. So let's look at a little pattern here. Oops. So alpha, we saw before, one of the generators of H1 is generated by these vertical lines. And it can be shown that, exactly for the same reasoning, beta, the other generator, is generated by the horizontal lines. And then we saw from before that alpha cup beta is generated by these points. And these points are actually precisely the intersections of these horizontal and vertical lines. So what this suggests, and there is some way of making some part of this precise, is that in general, we can represent the cup product H1 times H1 goes to H2 using this map of cycles. So it takes 1 cycles, and it takes the intersection, which gives you a 0 cycle. So you notice that in this map, the space, the torus, or whatever other space, none of that is mentioned here. So actually, this map represents the cup product for every single topological space out there that is nice enough. So a single map like this encapsulates the cup product for every topological space that is nice enough. Yes. So actually, I proved a generalization of this result. So if these cup products can be generalized into things called cohomology operations, which are ways of taking a cohomology class, mod P, for any prime P, and producing a new cohomology class. And every single one of these can be represented by a geometrically defined map between spaces of relative cycles. So these operations, they include cup powers, Box-Stein homomorphisms, Steenrod powers. They are very important in algebraic topology. Yes, so I'm almost out of time, so I'll just put a little advertisement that if you want to see more about how these maps are defined, what these maps look like, and why this representation works, please come to my talk next Tuesday at the Hausdorff Research Institute of Mathematics. Yeah, thank you very much.